In this problem we have water at 90 degrees Fahrenheit is being pumped from a sump pit at a velocity of 6.5 feet per second through the suction side of a pump. We are asked to calculate the theoretical maximum height the pump can be placed over the pit, giving the following conditions. We're told that the atmospheric pressure, so this is an open tank, open pit, is 14.25 pounds per square inch absolute. Vapor pressure of the water is 0.7 psia, and lost head in the suction pipe is equivalent to 3 velocity heads. So we have here a little schematic of our system. We've got our pit that is filled with water. We are assuming that the level of this is going to stay relatively constant, and we've got our pump that is located above this that is pumping the water away. So I've got some information that's given. I'm converting some of these things to SI units. So we've got the temperature of the water. We aren't going to need it, but I just have it written here. Atmospheric pressure, it's not 14.17, it's 14.25 psi. We're told the linear velocity of the water through the suction pipe, 6.5 feet per second. You look at that in meters per second. And then we're given some information. I went ahead and looked up, because sometimes in these books where problems are given there are errors. And so I went ahead and confirmed that the vapor pressure of water at 90 degrees Fahrenheit is indeed about 0.7 psi. I looked it up in NIST web book and it came out to 0.698. That's pretty close. I'm going to use 0.698 anyway. And then a lot of times for water we tend to use the generic the nominal density of 1,000 kilograms per meter cubed, or 62.4 pounds per cubic foot. But I went ahead and looked it up, since it is a little bit different from standard conditions. It is 994.9 kilograms per meter cubed. Now, what we want to know is what is the height difference between the level of the water in the tank in the pit versus a pump inlet. Generally, for these kinds of problems, there's two kinds of reasons why we would want to know that. Number one, we want to know if the pump is powerful enough to pull up this fluid and pump it away. That's not what we're asking for here, though. That's not what we're considering. We know that in this case the pump is powerful enough to be pulling the fluid up and pumping it away. We're going to assume that part is fine. The reason why we are doing this problem, this is actually a net positive suction head type of calculation. What we want to know is how high above the fluid level we can be before we start getting the water to boil inside the pipe at the pump inlet and cause cavitation. And so as the water is being pulled up, the pressure is going to decrease, and we do not want that pressure to get close to, actually we don't even want it to get close to, we definitely do not want it to reach the boiling pressure, which would be 0.7 psia. So that is what we are doing here. This is basically a net positive suction head type of problem. And so the way to do this is to set up a Bernoulli's equation where we have position 1, and I've already indicated it, is going to be the level of fluid in the tank, or in the pit, level of water in the pit. Position 2 is going to be at the pump inlet. Notice that the pump is not part of our system here. Our system is only going to go up to the pump inlet. So if I write my Bernoulli's equation, and again I like using Bernoulli's equation in the weight-based format, and so I write it for position 1, head added, head loss extracted, position 2. Velocity, let's look at these terms. What is a pressure at position 1? Pressure at position 1, the liquid level of surface, this is atmospheric pressure, right? What is the velocity at position 1? The velocity at position 1, well, that's going to be essentially 0. We're not told anything about how the level is changing. Even if the level in this system were changing, that change is going to be so slow. The velocity of the level going up and down is going to be so slow, it's going to be negligible. So we set that equal to 0. What about the elevation? Well, we're going to set our datum to be our reference level to be the level of the fluid in the tank. So that is equal to 0. Head added. Is there any head added to our system? And the answer is no. We do have a pump, but the pump is not part of our system, right? Our system goes to the inlet of the pump and then it stops. The pump is not part of our system, so there's nowhere in here that head is being added, so that's equal to 0. What about head loss? Head loss, this is due to friction in the of the flow in the pipes. We are not told anything about the inner diameter of the pipe. We're not told anything about the any kinds of fittings, valves, bends, or anything like that, elbows. But we are told that the frictional loss is equal to 3 velocity heads. And we'll your textbook talks about how to deal with that, and we'll talk about that in just a minute. But that's what our head loss term is going to be. There's no head extracted term, so that's going to go to 0. What about P2? P2 is going to be the pressure of our water at the pump inlet, and that is that is what we want to set as 0.7 psi. All right, so that is our P2. What about V2? That's the velocity of our water in the pipe at the pump inlet, and we know what that is. We're told that is 6.5 feet per second. Notice we weren't given anything about pipe diameter, we weren't given anything about mass flow rate or volumetric flow rate. We were just given the linear velocity straight out. And this may not be the best problem, but we do not know what the total mass flow rate is because we don't know what the pipe diameter is. But that's okay, we can still solve this part of the problem. Alright, so we know the V2, and then the Z2, this is what we want to solve for. Alright, we set P2 equal to the vapor pressure of water, and then we are solving for the elevation difference, which is Z2, between the pit level surface and the pump inlet. So this is our Bernoulli equation. What we can do is we can solve for Z2. We can rearrange it, solve for Z2, and get our answer. First thing we have to do, though, before we can get our answer is we have to do the dimensional analysis for the head losses due to friction. We're told that there were 3 times the velocity head, or 3 velocity heads. So the velocity head, that's just the v squared over 2g term, all right? And so again, this is why I like working with head units or energy per weight, because the velocity term is going to be the velocity, or the velocity head is going to be the velocity in the pipe squared divided by 2g. So we plug our given value in and we calculate the velocity head, and that is equal to 0.2 meters. That's 1 velocity head. All right. Now the total head loss is going to be 3 velocity heads, so that's going to be 3 times 0.2, which will be 0.6 meters. Now we can take this information, we can substitute, we can simplify our Bernoulli equation, solve for Z2, and so I'm doing things kind of step by step here, not skipping too many steps. Now I've got my P1 term, I've got my 3 times velocity head for my head losses, P2, V2, Z2. We can solve for Z2. Notice I set P1 equal to the atmospheric pressure. I set P2 equal to the vapor pressure of water, 0.698 psi. We can solve for Z2. Once we solve for Z2, we get 28.793 feet. So what that means that if our pump is 28, assuming everything here is as we assumed, if our pump is 28.793 feet, the water will be at a pressure of 0.7 or 0.698 psi at the inlet. That means that the water is going to be boiling. right? That means that the water is going to be boiling. You're going to have bubbles forming, and then once they get inside the pump, they're going to get cavitation. You're going to tear apart your impeller and the insides of your pump. So that is the that is undesired. So of course, what you would want is, number one, you would want to know what the NPSH-A of your pump is, and that's pump specific. We're not given anything about that, but then you would want to go through your calculations and then make sure that your pump is much lower than that, so that you're avoiding any chance of cavitation of the water in your pump.